Hello everyone. I just wanted to sort of throw together a video about memory today. So this is completely impromptu. I'm just going to be sort of talking as I'm looking through this. So it might not be super polished, but hopefully this will be able to help you out in understanding memory and how to build complex memory. So at this point, I'm assuming that you're familiar with D-latches, as they're essentially the primary method of building memory. It's way easier to use D-latches than something like an SR latch or anything like that, mostly just because of how you can interact with them. But yeah, so just a quick overview of D-latches. So for the purposes of building memory components and larger memory components that have addresses and all of that, we can imagine D-latches just as being some box, has a D input, has some sort of clock input, and then an output Q. And what's important to remember is how the state is updated. So let's say we have D, we have the current state, and we have the clock, which I'll just abbreviate with C for now. And we want to know what the next state is going to be. And so you can think of the truth table as completely like this, and I will work it out. So here, if we start off, so if the current state is 0 and the clock is 0, and namely we can just look at this clock here to determine what's going to happen. So if the clock is 0, the next state is just going to be the current state. So that is always the case. If the clock is 0, next state is the current state. So here the clock, I'll probably change this to 1. So here the clock is 1, which means now the next state is going to be whatever D is. So essentially you can sort of think of it as whenever the clock is 0, the next state is the current state. Whenever the clock is 1, the next state is D. So here D is 0, so that'll be a 0. And we can look at the next configuration. Here the clock is 0, so that means we're going to choose the current state, which is 1. Then we can choose, then we have the next option here. So when the clock is 1, we'll choose D, which is 0. And we can sort of continue filling out this table. But this table is a little bit big, and it doesn't really help you to get a good understanding of exactly how a D-latch works. So instead, I typically prefer this sort of table. So here we have all of the different options for D in the clock. And then we have the next state. And here, instead of having a column for the current state, I'll just write it in if it's necessary. So when the clock is 0, the next state is going to be the current state. When the clock is 1, it'll just be whatever D is. So here we still have the current state regardless of what D is. And then lastly, we have this. And even you could describe it even simpler in saying, well, when the clock is 0, the next state is the current state, and when the clock is 1, the next state is D, whatever D is. So however you want to think about a D-latch, it doesn't really matter. But what's important is that a D-latch stores exactly 1 bit of information, right? So we can give it some sort of input here, and then depending on whatever the clock does in order to update that state, it'll just, when the clock is 0, it'll just keep its current state. It won't change. And when the clock is 1, it'll read what D is and update the state to that. And so these store single bits. And obviously, that's a big step from not having any sort of memory. But what happens when you want to store numbers, full binary numbers? How could you possibly do that? Well, really, it's pretty simple, right? How would you store multiple numbers together in any sort of programming language? You just create an array, and you can just put different values in each location in the array. And essentially the same thing happens when you're trying to go from storing a single bit to storing maybe a byte of information or a 4-bit binary number. I'll just go with 4 bits because it's relatively small, but keep in mind that all of these are just expandable fairly simply to a larger number of bits. And as we're working through memory, that's one of the biggest things that you need to know and be able to understand, is that everything can just expand. but there's potentially certain rules that you need to follow when trying to expand something. So if you're trying to go from a smaller memory component to a larger one, you need to be able to understand what needs to change, what needs to get added, and all of that, so that you can actually create the larger memory component. So we'll just start here and saying, okay, well, we have a bunch of D-latches, and for the most part, unless stated otherwise, a box, just some generic box like this, is just a D-latch. So here, suppose that we have just 4 D-latches, and suppose we have our number A coming in here. We'll just say here, and this is a 4-bit number. So this might be new notation, but if ever you see sort of a wire like this with a slash through it and a number, that means that this is actually not just a single wire, but it's 4 wires that are sort of tangled together. They're tied together essentially permanently. And so what we can do here is we can take one of these bits off, and we'll call this bit maybe A3. Just say the largest bit of A. So A sub 3. And then we can continue on all the way. And for each of these, we can just take off one of the extra bits. So, this would go down to 3, then down to 2, and then down to 1. And this we might call A3, A2, A1, and A0. And then, so these here would be the D inputs of all the latches. And then the clock here, we can just take for each of these and wire all the clocks together. And that way, whenever we activate the clock here, it'll just store all of the values of A. It'll just store the largest bit in this D-latch, the next largest bit in this one, and so on. And if our number was 8 bits, we would just add more D-latches in this direction, right? We can just continuously expand that to as many bits as we need. And all we've done is just connect a whole bunch of D-latches together by their clock. And it really is just that simple. Now we can store numbers. And in general, this component here is called a register. And I'm sure you've heard that as we've been talking about, actually I might draw this a bit lower. We've been talking about this in regards to computers and saying, oh, well, you're accessing registers and so on. And those are specific registers. Those are, the general purpose addressable registers that exist inside of the core of a CPU. But this is just sort of a more generic register where I can have some n-bit number coming in, and then the output, which will also be n-bit, and then just a clock. And what it'll do is it'll take some n-bit number and just store the entire number in that location. And that's what a register essentially is. It's just storing a number. And we can very, very easily create them just by basically attaching the clocks of several D-latches together. Fairly simple. And so this is the first step. Remember, we've now increased the width of the data we can store, right? But now it's not really useful to just be able to store to one location and only one location specifically. We ideally would want to be able to have multiple locations and be able to specifically say, hey, go to this location or go to this location. Sort of like an array, right? Let's say we just imagine some massive array of numbers. We'd like to be able to say, okay, put this value in the array at 0, this value in the array at 1, this value in the array at whatever, right? And we have no ability to do that because we have no way to basically specify what index we are writing a number to. And so that's the other part of memory. So this is the first part. The first part is the ability to increase the width of our data. And to do that, you basically just extend sideways and you just connect things together. It's very, very simple to extend the size of your data. To extend the number of locations that you can write to is a bit more complicated. And we really need to start off somewhere. We'll start with a very basic component before we can really start creating more complex components out of those. And so let's move down here. So let's say we're again just dealing with 4 bits to make it simple. And let's just think, okay, well now what happened? Let's say we want to have 4 different locations we can store a number to. So essentially we're trying to create in hardware an array of 4 integers, of 4-bit integers. So we can have one register here. And the typical way that this is drawn is left to right. This way will basically be the size of your data. So if you have 32 bits, then you'll want to somehow build those left to right. And then if you have multiple addresses, you'll build that up and down. There's not necessarily any particular reason why this is how it's typically drawn, but it's just the way that you want to try to always draw it, because it's the way that everyone's going to expect you to draw it. So we will have 2 registers, 3 registers, and then 4 registers. So we want to be able to say, okay, provide some way to specify which of these locations we want to write to, and then we want to have one input D here that will write to a specific location. And D here is going to be 4 bits in this example, but it really doesn't matter. It could be n bits. So how could we possibly choose a location to write? Well, I've chosen 4 here because it's a power of 2. And as with most things that deal with architecture, anytime you deal with a power of 2, it's generally easier, and also likely has something to do with binary. And the most information dense way that we can actually provide an address or a location, right, specify which one of these that we want to write to, is going to be using a binary number, right? Here, because we have 4, if we provide a 2-bit input that we can call the address here, if we provide it only 2 bits, well, those 2 bits could either be 00, 01, 10, or 11. And we can easily just say, okay, well, if this address here is 00, we want to write to this one. If the address is 01, we'll write to this one. If the address is 10, we'll write to this one. And if it's 11, we'll write to that last one. And so that's typically how this memory is going to work. And if you've worked with any sort of low-level programming languages, especially down near the assembly level, you'll know that accessing memory is as simple as just specifying one of these addresses and then reading or writing from that location in the memory. And so these here are those locations. And we specify those just with a binary number because that's the densest and the easiest way to do it. We couldn't use less bits, right? If we only used 1 bit, we can only specify 0 or 1, which isn't enough for 4. And so binary is going to be the most efficient way to specify where we're writing. So now we need some way of being able to specify which of these we write to. Now, one thing that you really should keep in mind is how the clock works. When the clock is 0, the register will not update the value. It'll just stay whatever it is. So suppose now we just take this data here and we just wire it up to every single one of these registers, just as the D input to the registers. Well, if the clock here for all of these is 0, well, nothing's going to happen. So we can just wire this input to all of them without really needing to worry about anything. And we can then use the clock and only the clock as a method of controlling where we're writing to, right? If we want to write to this one, then all we have to do is set this line to 1. If we want to write to this one, then all we have to do is set this line to 1. And that way, and keep the rest of them 0, obviously, because if the rest of them are 0, then all of these will just stay the same. And if we set this one to 1, then it'll take this value of D and write it here. And so now all we need to do really is have some sort of clock input. And for any sort of memory, you're going to need to have some sort of clock to synchronize when things happen. A lot of memory is based off of delays occurring, especially like SR latches. You need to have some sort of delays with how long the gates take to actually propagate and compute values. And in general, in a computer, having a clock is going to help you synchronize the when something happens, right? We wouldn't want to just provide any sort of data and any sort of address and then the memory immediately write to that location, right? Because then if we change the address again to something else, it would also immediately write. And so we'd have to change the address and the data at the exact same time to be able to write the new information correctly. And that just gets way too complicated. And so instead we can just have a clock, and we'll say when the clock is 0, don't do anything. Just sit there and do not actually write anything. But when the clock is 1, it'll actually write something. And so now, when this is 0, we essentially could send zeros to all of these, right? Just because this is 0, and that will just maintain the state, not update anything. And then when the clock is a 1, well, then we want to specifically route the 1 to one of these locations here. So how do we do that? Well, for those of you who have a little bit more experience with basic circuitry, this is the exact location where a demultiplexer would be ideal. However, if you're not familiar with a demultiplexer, we'll actually want to use 2 different components to effectively create a demultiplexer. So the first one is going to be a binary decoder. And so all that's going to be is it's going to take the address here and we'll pass it into a 2-bit binary decoder. And all this is going to have is 4 outputs. One will be an output when this number is 0, 0, 1 for 0, 1, 1 for 1, 0, and 1 for 1, 1. Now, you might be asking, well, how do you build a decoder? And really, you already know how to if you've made a multiplexer. Because essentially all you do here is you would just have your 2 data inputs. So this is a binary decoder. So you take your 2 inputs, maybe A1 and A0, and then we'll just branch off of here and say, okay, well, if they're both 0, by inverting them, we can AND that together. Well, that'll be that first input, right? So when these are both 0, this will be an output. Then when this one is a 0, and this one is a 1, well, this one will be on when the inputs are 0 and 1. And we can just continue. It's essentially just building a very basic sum of min terms expression, but for each individual thing. So it should be fairly simple to create a binary decoder. And that essentially allows us to convert from a binary representation to sort of a representation that exactly points to where we're at, right? Right, it allows us to basically say, okay, we have this input 0, 1. Well, which of these numbers is it? Well, 0, 1 is that number. And we want to be able to point to that in the same way that we say, okay, well, when the input of the address here is 1, 0, we want to write to this location here. And so that does that work of selecting which of the actual registers we're writing to. And now we just need to synchronize whatever the output of this is to the clock. And we can do that very easily with an AND gate. Because here, if we think of the clock, we'll wire that up here. So when the clock is 0, the output here is obviously going to be 0 because 0 and anything is just 0. But if it's a 1, and coincidentally, the address here that we're specifying by A is 0, 0, then we would have a 1 here, which would mean a 1 here, which means we would actually write to this location. So when the address is 0, 0, and the clock is 1, then we'll write the data to the first one. And that's precisely what we want. And so if we just continue to wire up the rest of these, we'll have an AND gate for each of the registers to essentially specify whether or not we're writing to that register. Then we'd have the clock as one of the inputs to these registers, to these AND gates. And finally, we would wire up all of these here to the AND gates. And hopefully this isn't too cluttered and you can see what's going on. But we're just taking the output of the binary decoder and ANDing it with the clock. And that allows us to have the clock as a control to control whether or not we're writing. And this makes up essentially all of the portion of the main memory that deals with writing. This allows us to select a location that we want to write to and write to that location using the clock. And it doesn't really matter what the data is, it'll work. And keep in mind, these here are just registers, which are just a set of D-latches with the clock attached together. So that way, when you write one bit, it writes all of the bits simultaneously, so that way you're never breaking up the number that you're looking at. So now we would want to be able to read from these locations. And if in some cases, reading from these locations would be simple, right? You could just take an output from each of these and just pass them to whatever you need it to be. But for a general sort of memory component, you want to be able to read and write data from the same data bus. And that's a little bit bizarre from the perspective of digital logic, right? But from an electronic perspective, it's much more efficient to use the same bus to pass data in both directions. At least space efficient and heat efficient. So here we'll say that, let's say we have the output Q, and so we're going to have 4 different Q outputs. But what if now we want to be able to choose one of these locations specifically to output, as opposed to just all 4 simultaneously? In the same way that in assembly you might read from a specific location, you want to be able to get the data from that location and sort of put it into one specific place, right? Not have 4 different outputs that you can't really do anything with. And so, but we also want to use the same bus, which does complicate things a little bit, but we'll see how we can get around that. And so additionally, as an input to our memory, we're also going to have a line here that is a read-write line. So here, whenever this is a 0, we'll just be reading. And whenever it's a 1, we'll be writing. And so we can call this the not read write line because, well, if it's a 0, then we have that, write equals 0 and not read equals 0, which means read equals 1. So when this line is a 0, we're reading and not writing. But when this line is a 1, that means W will be 1, which means we're writing, and not read here will be 1, which means read will be 0. A little bit bizarre of syntax, but it should make sense. And so, well, now we somehow need to make sure that we're not doing anything when we want to read and exclusively want to read. And so for this, we can fairly easily just inject an AND gate here and say, oh, well, if this line is a 1 and the clock is a 1, then we'll actually perform a write, right? So, and a write is essentially just powering this line because the address will always be selecting something. And so, yeah, we essentially have a thing that allows us to choose whether or not we're reading or writing. We haven't implemented the reading yet, but we can go ahead and do that now. So, to read, we need to choose between some of these options here. And whenever you hear that sort of, I need to make a choice or I need to choose some sort of output, the de facto thing that you should think about when dealing with circuitry is a multiplexer. That's exactly what they're meant to do. They're meant to take in a bunch of inputs and another input to select which one of those that you want, and then output that. So the issue, however, is that we actually have multiple outputs here. We don't just have 4 bits, we have 4 4-bit numbers. And so we actually need multiple multiplexers to be able to choose between the correct bits of everything. And so we'll just consider now, let's say, Q3 output for all of these. So the largest bit. Well, how can we choose which one of these that we want based off of the address? So for reading, what we want is when the clock is 0, we're not doing any sort of reading. Again, the reason for that is we don't want to do anything when the clock is 0. when R is 0, and when this line here is a 0, that means we do want to be reading, and the clock is a 1, then we want to look at the address, whichever register, at whatever address is specified, and then take that data and output it on this D line. And so this line here is actually going to be bidirectional. So how can we properly choose which of these is correct? Well, with the multiplexer here, all we have to do is take this address and pass it in as the selector lines to just a small 2-variable multiplexer. Right? So we can take this input here and wire it up to the I0 input, and take this one here, wire it as the I1 input, take this one here as the I2 input. This is a bit small. And then finally take this one down here as the I3 input, with the selector lines being the address. So now, based off of what the address is, we will select either the Q3 bit from this one, the Q3 bit from this one, or the Q3 bit from this one, or this one. And so the output here is going to be the Q3 bit that we want to read from the address that we want to read it. What do we do with the rest of the bits? Well, we'd have Q2 here, and so on, and then we take the outputs of all of these, and those would all go to another multiplexer, whose selector lines are also these address bits here. And keep in mind, this is 2 variables, so all of the selector lines will just be whatever the address bus is, because we're using the address to choose which of the bits that we want from which number that is stored. Keep in mind that you're not taking all of the bits from a single register and passing them all as the different inputs of the multiplexer, because if you do so, you're only going to be choosing one of the bits of your number. It's like saying, okay, well, I'm going to store this number into the memory, and I'm going to store this number somewhere else. And then, okay, well, I want this bit from this number, I want this bit from this number, and maybe this bit from another number, and then combine those together. That doesn't make any sense. Right? We want to either choose all of these bits or all of these bits or all of these bits and so on. And so you want to think about that every time you're designing these. I haven't made any sort of big leaps, right? We used a binary decoder to take the address and basically choose what location we're writing to. And now we're using a multiplexer to choose which of the bits we want to read to. These are all fairly straightforward things. And as long as you keep that in mind, it should be fairly obvious how to construct a memory block or whatever it may be. And so here we'd have one for Q2, one for Q1, and then finally one for Q0. And I'm just not going to write that because it will be a massive jumble. It is a complex circuit, definitely, but I'll just omit trying the rest of those because it would be rather complicated. So now this is constantly going to be outputting a number based off of what address is, right? Because these registers have no ability to prevent them from being read or not. So we need a way to basically prevent an output from being created. Now this is where we sort of step slightly away from logical components and logical digital components, and go a little bit more into the world of electronics. And we're going to use something known as a tri-state buffer. And this, for the purposes of 3181 at UNCC, don't really need to get too much into how they work, but you can just think of them as sort of like something that a component that can physically disconnect wires at will based off of a control. So we draw a tri-state buffer just as a normal buffer, which is just a triangle, no circle at the end. If you put a circle at the end, that's an inverted buffer, which is just a NOT gate. And so we draw just a triangle, and then we'll have a secondary input coming into the side. We'll have it coming at the bottom here. And this input here, basically, if it's a 0, nothing's going to go through. It's just going to completely almost cut these wires completely off. But if the input is a 1, then it'll connect that wire, and the output of these Q3s would be able to pass through. Now, when do we actually want to have this output? Well, we want to have this output when we're reading and when the clock is 1, because again, we don't want to do anything if the clock is 0. So if we take this clock input here, and we take this read-write signal here, and bring them all the way over here, well, when we're reading, this line is going to be 0. So if we invert that, and then pass both of these into an AND gate, well, now when we're reading, this will be a 0, which means we'll invert it into a 1 into this. And then when the clock is a 1, this signal will be a 1, which is precisely when we want to produce an output here. Otherwise, like if the clock is a 0, then this will output of 0, or if we're writing, this will output of 0. And so we can just take this output here and put it directly as the secondary input of the tri-state buffers. And that way, only when we're reading are these wires here going to actually be connected to these. And then all we have to do is combine these all back up into single 4-bit number and connect these back up to our input, right? Because essentially, although the data might be coming in this way, it would come down here, and then it would also come around over here. Well, it can't get back through, because if this input here is a 0, these will all get disconnected, and so it's not really going to do anything. The actual data is not going to come back this way. And then when we're reading, the data would be coming out here, and you might think, oh, well, it's coming back here. But keep in mind that this value here has to be a 0 for this to output anything. And if this is a 0, then this input here is a 0, right? Because we're reading and not writing. And so we're not actually going to pass a 1 here to do a write. And so all of the inputs here to the registers are going to be 0, which means that we're not going to write anything. So there's no problem in that data getting sent over here, but it allows us to use this wire in 2 directions. And this is a memory component. That's it. There's really not much more to this. The next step of this is, let's say you were given one of these components in a box, just in a box, right? It's a component that some manufacturer makes, and you want to make a bigger memory component. Well, we've already done that in one sense, right? We started from a D-latch and built up, but now we actually have all this stuff. We have these multiplexers, we have these buffers, this decoder, and all of this logic for the clock and the read-write, and so it'll actually be simpler to go up from one of these to something a bit more complicated. So let's see, I'm going to move down here, and I'm going to assume that we just have some of these components here. Right, so we have a box that will accept, I'll make it a little bit bigger because there'll be quite a bit in this box. So we'll assume it has the data input up here. We have the address, we have the clock, and then we have this not read write signal, and then we have our output. Well, there's no output Q, right? So now we only have D. So in this case, if we're trying to make something out of these blocks, we don't have to worry about Q, because D is the only thing that actually gets interacted with. And that makes it quite a bit nicer to actually deal with. So let's say we have an 8-bit number coming in and a 4-bit address. And let's just pretend as though we don't have all of those individual components that we could be using, right? We don't have any of these individual components necessarily. All we want to do is use these pre-built components to create a memory component that can support an 8-bit data bus and a 4-bit address bus. Okay, well, here we have a 4-bit data bus, right? And the same thing as with the D-latches. If you want to be able to support more data, just add more things and make sure that whenever something happens to one of them, it happens to all of them, right? So we can just take one of these components here and put it over here and say, okay, well, this will be for the higher order 4 bits, and this will be for the lower 4 bits. So if let's say we want to write that number here, we would just take these 4 bits and write it here, these 4 bits and write it here, and that's it. Same way as with the D-latches, if you want to store multiple bits, you just stack them together. you just do that here. And all we'll do for the address here is connect them together. So this will be a 2-bit address, because remember this is a 2-bit here. And then that'll come all the way over here. Also, the clock is just going to be hooked up as well. And the read-write is also going to be hooked up. And so now we've actually created a memory component, just these two here, nothing else, is an 8-bit, it has 8-bit, can support 8 bits of data and a 2-bit address bus. So to increase the number of data bits that you have, again, just increase the width and make sure that whenever one thing happens to one, that happens to all of them. And that way, those bits will always be tied together. And really, it's almost like you have two 4-bit numbers. And in fact, that's what's going on here, because you're splitting up a large 8-bit numbers into two 4-bit ones and storing them individually. Then when you read them, you can just have these, and then you can just combine these two together in a single 8-bit wire, which is essentially what's going to happen, right? We can take this data line here, pass it all the way over here. We'll take, well, some of those 4 bits will come down here, and the other 4 bits will come down here. So this might be, you know, D7 through 4, and this might be D3 through 0. So now we need to figure out some way of actually managing this address, right? We have 4 bits of address, but we only have a component that can support up to 2 bits. Well, we can do a very similar thing as with the normal memory component up here, right? We can decode some of these bits to choose a block, some sort of memory block to write to. And so we can make more of these down here. I'm going to draw less just because it gets tedious. So we're going to have a clock, and we're going to have a read-write here. Or actually, really, we'll have a read-write that's sort of global. This will just go to the read-writes of all of these, because we're either going to be reading from all of them or writing from all of them. Never both at the same time. Or doing different things at the same time. At least not for a basic memory component. And so this one I'm just going to assume gets wired everywhere. I'm not going to bother actually writing it out, because that would get kind of ridiculous. So we have the clock, we have the address, we have data. And we'll, actually I can just make a copy of that. So now we have 2 of these again. And again, we'll just connect the address up together. And we'll connect up the clock together. And keep in mind, there is the read-write. I just haven't drawn it. And then we can continue making more and more of these. Oh, actually, I believe I need to merge these together. There. So now I can take this, make a copy, bring it down here, and then make another copy and bring it down here. There. All right. So why have I created 4 of these? Well, if we think of it, we can, each of these banks here now can support 4 different addresses, the same as above, right? Because there's a 4-bit location here, there's 4 4-bit locations, 4 4-bit locations, and we've combined them sideways in order to create 4 8-bit locations. But our address here is 4 bits. And how many different numbers can we create with 4 bits? 16, because 2 to the power of 4 is 16. Right, so we can do 0, 0, 0, 0, 0, 0, 0, 1, and so on till 1, 1, 1, 1. And that is 16 different numbers. And so if one of these banks here can support 4 addresses, well, if we have 2, that's 8 addresses, then 12 addresses, 16. So we need 4 banks here to actually be able to use all of these, to be able to support all of these addresses. So how do we do that? Well, we need to sort of lay out some of these addresses across all of these. So let's just state, and we'll design it this way that the first address up here will be the address 0000, then 0001, then 0010, then 0011. Then down here it'll be 01, 0001, 01, and so on. Then it'll be 11, 10, 00, and the other 4 there, and then 1100. And what you'll notice is at the beginning of these, the first 2 bits are always the same in all of these banks. And then these lower 2 bits here can essentially be used to address within these. And so this gets into a concept of sort of like multiple levels of addressing. And so what we can do is we can take like the higher order bits to basically figure out which of these banks we want to write to, and we can use the lower level bits to figure out within these banks which of the locations we want to write to. And by doing that, it should be fairly simple to actually implement this. And so really all we need to do is decide on a way to figure out which of these banks we want to write to. Well, the lower bits are always going to be used to address which within each bank. And so we can just take the lower 2 bits, and that'll be these 2, and this can just get connected to every single one of the address lines. Because regardless of which bank we choose, we're always going to pass those lower 2 bits into that bank. And again, rather than trying to control where we're sending the address, we'll just send the address everywhere and then manage which one of these banks we're writing to using the clock. And that's always going to be the best strategy because the clock is a single wire that can be controlled a lot more easily than a whole set of wires. And so we can ignore that for now. So we'll take these lower 2 wires. Okay, well, we want to somehow be able to say, okay, well, if it's 00, it's these. If it's 01, it's these. If it's 10, then it's these. If it's 11, then it's these. And that same sort of, if it's this number, then I want these from that last component, that should tell you about that should signify to you that you should use a binary decoder. So here, if we use a binary decoder, we'll have the 00 output, 01 output, 10 output, and 11 output. And so now, when the higher 2 bits are 00, this wire will be on. If it's 01, this wire. If it's 10, it'll be this wire. If it's 11, it'll be this last wire. And so, well, now, how do we choose which of these banks to write to? Well, if we just send the clock signal to the set of which bank we actually want to write to, well, that's effectively the same thing as choosing which bank we want to use. And so we'll have our clock signal here again, and also that not read write wire, which is again going to all of them, but there's no logic. It's just that wire gets connected to all of them. It would just create some extra hassle to do so. And so we have our clock signal coming out of all these. And again, as with the same with the last one, we'll place AND gates coming into all of these, with the clock signal being one of those inputs. If we would just wire this clock signal to the clocks of all of these, then we'd simultaneously be writing to all locations, which isn't useful because we would write the same thing everywhere, and we would effectively only have 4 locations just with like 4 copies, which in some situations might be useful for redundancy, but for just creating a basic memory component, that's not going to be very useful. Then we can just take these last wires here and AND them. So now when the higher 2 bits of the address are 00, which is this case, well, this wire will be on. Now, if the clock is also 1, and we are writing or reading, it doesn't really matter at this point because all of the logic for handling reading versus writing was all done up here, right? We have this wire that allows us to do that. And so if we're using one of those components that already has all that logic built inside, we don't need to add any externally. So it doesn't matter whether we're reading or writing, but if the address is 000, let's say 0010, well, if it's 0, because the higher 2 bits are 00, this wire will be a 1. Well, the clock is obviously going to have to be 1 because we're doing something, right? So this clock will be 1, and it'll activate both of these. So for writing, well, the data, the high bits, the high 4 bits will be written to here, and the low 4 bits will be written to here, where which one of the addresses within this component it'll write to is going to be determined by the lower 2 bits, right? Because we're sending those in to both of these components. So we'll have that. Then we'll have this second wire here being wired up to the second bank, the second set of addresses, third wired here wired up to the third set of addresses, and lastly, the fourth wire here being wired up to the fourth set of addresses. And this will implement a memory component with an 8-bit data bus and a 4-bit address bus out of these smaller memory components that we've been given. But if you noticed, there wasn't really anything different about doing this as there was for doing this, right? Essentially, all we did was implement this stuff over here, and all of this stuff we didn't even need to worry about, right? So the concept of being able to take the address and splitting it up into the high bits and low bits, the low bits used to address within a bank, and the high bits to address which bank you want to use. Well, here, there's no addresses within the banks, so we're using all of the higher bits to address which bank we want to write to. And so there is fundamentally no difference between designing one of these and one of these. The only thing is that this is slightly easier because some of the work's already been done for you. Now, this is perhaps a bit more complicated than what you'll probably see in the course, and that's just because we tend to simplify that a little bit. So if we again imagine that we have these components. So here we have D, we have our address, and we have the clock, and also the read-write. That's going everywhere. Well, instead of having the clock, we'll just wire the clock to everyone, to every single thing, and we'll just have another input known as the Chipselect. And essentially all the Chipselect is going to do is enable or disable the component, but it's separate from the clock. It's almost like a second clock input. So if either the clock or the Chipselect are 0, nothing is going to happen. Both the Chipselect has to be 1 and the clock has to be 1 to do anything. And so if we absolutely wanted to see how that would be implemented, well, we'd essentially just have a clock input and the Chipselect input, and we just AND them together right here. And the output would just be connected to what would normally have been the clock input. So that way, the only time that this component here will ever work is when the Chipselect itself is a 1. And this is just an AND gate here, right? And so essentially what it is it's these AND gates here. So rather than having to draw out all of this component here, we'll have a Chipselect inside of this that allows us to select which chip that we're using. It's just a little bit of a shorthand that we use in the course to simplify things slightly. And so we'll still have our 2 bits wide here. I'll go ahead and merge those two. Then we have our address getting wired up. And well, again, we'll wire up the Chipselects between these two because, again, we want these two things to do the same thing always. We never want them to be doing different things because they represent the high and low bits of a single number. And again, the clock and the read-write, those would be wired up somewhere, right? Don't really need to specify how those would be wired up because there's no logic. It would just go to every component. Then we would have multiple of these, again, because we have several of those. Oh, that's not, let's see here. Go and merge those. Now I should be able to copy this. There. So then that'll be our second bank. Then our third bank. And lastly, our fourth bank. And so again, our data line would come up here. It'd get wired up to every single one of these. And I think I did potentially forget to do that. Yeah. So another note here. This data input would again just be wired up to every single one of them. And that's the same principle as the last component. where, again, we're not going to worry about the fact that we're sending the data at everything. We're going to use the clock signal to control where things are happening. So here again, we're just going to send the upper 4 bits to all banks, the lower 4 bits to all banks, and just leave it at that. So here we've got this data coming there. So we have our data, which is 8 bits, the upper 4 bits here, the lower 4 bits here. Or the other way around, it doesn't really matter as long as you put them back together the same way. So we have our 4-bit address bus, and only 2 bits are going to come here. And it technically could be the lower or the upper, or any combination. It doesn't really matter which 2 bits, which is why there's not really a point in specifying it. Doing the lower 2 bits and the upper 2 bits and keeping everything in order means that address 0 is up here, then 1, then 2, then 3, then 4, or the 0, 1, 2, 3, then 4, 5, 6, 7, 8, 9, 10, 11, and so on. But if you use any other set of bits, it just might be like, oh, address 0 is here, then 1 is down here, then 2 is here, then 3 is here, then 4, 5, 6, 7, 8, 9, 10, and so on. It ultimately don't matter. It doesn't matter. It will still work. So yeah, we would set the upper 2 bits here, or lower 2 bits, take these 2 bits here, pass them into the binary decoder, same way as above. But now, instead of having to do these AND gates with the clock, we would just wire all of these to the chip selects. And keep in mind, this drawing right here is identical to this one here. It's just this one, we're assuming that these don't have the chip select, so we have to manually create them outside here. And this one, we've just assumed the chip selects are built into these chips here. And so we could just wire up that. And also, again, we'd have the address coming down to all of these banks. But yeah, as far as memory goes, and as far as we'll cover it in the course, it doesn't really get much more complicated than this. You're either going to really be asked draw this, or be asked to draw this given one of those existing components. Sometimes you won't necessarily be able to draw the registers. You'd have to draw each of the individual D-latches. But again, you would just draw all your D-latches, connect the clocks up together, and that's it. There's nothing special about the fact that this is a register, because a register is just this. And again, I haven't drawn the outputs here, but there would be all of your outputs. So yeah, that's pretty much it for memory. So if you have any questions, feel free to post it in the comments. I'll try to answer if I can. But other than that, I hope you learned something new.